Hello everybody, and welcome to this session about a data storage diode for classified sites. So I'm Jean-Baptiste Rio from Kalray, located in France. So Kalray at SDC 20 this year will be presenting four sessions, and mostly about NVMe-oF and composable architecture. So you will also meet my two colleagues, Jean-François Marie and Rémi Coguet, during the three next presentation. So this presentation is about a storage diode. So the needs came from one of our customers, which had very specific needs for its site. So the site is a dark site. I will define what is a dark site a bit later. And they needed a solution to push data outside the dark side to the outside world in a secure way. And we will see all the constraints which were defined a bit later. But the idea is really to have a dedicated path with guaranteed read-only access from the outside world to some data pushed on a node on the dark side. As I said, I'm Jean-Baptiste Rio. I'm a senior field application engineer in Kerberos for the data center business unit. I came from the HPC world because before joining Kalray, I was in DDN and Intel, doing mostly SAN deployment, file system installation, benchmarking, troubleshooting. And also I joined Intel to do only Luster for a couple of years and support for a classified site in France. So some context about classified site and HPC. So what is an HPC dark site? So a dark site, first a dark site is a classified data center closed from the outside world. And the HPC dark site, it's an HPC cluster in a data center which is closed from the outside world. So it means there is no internet access. People who can enter the site are selected and filtered. And so an HPC cluster is basically a compute cluster sharing a unique file system between all its nodes. We will find thousands of compute nodes or client nodes connected to a parallel file system through IO nodes. These IO nodes generally are separated in two types of nodes, metadata server and data server, and they serve file systems such as Luster or GPFS or BGFS. And the sizing is multiple petabytes of data for the largest sites in the world. For a few years, we also find sometimes GPU farms and specialized nodes for AI workflows. So the challenges on the dark side is that as there is no internet access or no VPN access, it's not easy to push data outside the dark side. And as you are certainly aware, dark sites and HPC dark sites are very often collaborative sites, and a few users or few companies have remote access to the cluster, so they will generate data after all the compute is done, and the generated data is not intended for internal use. People using the HPC compute cluster needs to have access to their data outside the dark side. The way we can take some data out of the sites are very limited today. So you can do a control copy on drive. So it means that the researcher or scientists have to extract all the results they need from their experience, and it has to be controlled by a third party and validated so the drive can be off-site. You can also find sometimes special nodes outside for remote copy using a multiple layer of encryption. So I'm thinking about dedicated nodes outside the dark side connected to the dark side through an IPsec tunnel or this kind of thing, where you push only encrypted data. And very often we find also a direct optical link between the dark side and outside the site. So very often a close location, maybe a few hundred meters from the dark side. So a direct link is a secure way to push some data outside. So what is an HPC cluster? So a few words about that, just so everybody can understand what we will be speaking about. So this represents a typical HPC cluster. On the left, you will find the compute nodes, which are interconnected between them through InfiniBand, which is serving the Lustre or GPFS or any other parallel file system from data and metadata servers. These servers will be connected to a SAN storage, such as FBOF, JBOD, to serve the data. Between this type of server and the storage, we will find technologies such as SAS, fiber channel, simple LDAP protocol, or NVMe. Also, all compute nodes and IO nodes are connected to an admin network, which will be operated internally in the dark side. And so, of course, to do a storage diode, we can't afford to have a node connected to the same network. It would be a security issue. And so what is an HPC file system? So an HPC file system is basically a file system shared between all compute and client nodes in the HPC cluster. They really see one namespace which is unique between all nodes. Sometimes between the parallel file system servers and the compute nodes, we'll find a burst buffer, which allows to have tons of performances for small IOPS, which is not the best use case for HPC file systems. So about the technology, between the data server and the storage, most of the time we will find a fabric, or sometimes it can be also a direct attached solution. And for the metadata servers, it's usually only direct attached systems, such as a JBOF or FBOF. So the limitations we faced for the diode requirements is that we can't be connected to the parallel file system. The outside node can't have access to the parallel file system namespace, which is kind of obvious. It can be connected to the same admin network. It would be a security flow. And also, it can be a file-based access protocol. So it means it can be network-based, so you can't have classical, CIFS or stuff like this encapsulated into IP to push this out in the outside world. So the only remaining solution was a block-based access solution. So how can Kalray help with this project? So let's speak about our last processor named Coolidge. So Coolidge, compared to the traditional CPU and GPU approach, is a fully programmable processor. Its name is MPPA. We have a control plane and a data plane, which is based now on SPDK. And we target to be an open platform before the end of year, so our partner can contribute to the code base, and the code base can grow in the near future. The chip Coolidge is composed of 80 cores, which are gathered into 5 clusters of 16 cores. Each core runs at 1.2 gigahertz. And also each core, which is very important, embark a crypto accelerator, so which allows us to develop features such as erasure coding. Each core is a very long instruction word 64-bit core, as you can see here on the schema. A cluster is composed, as we said, of 16 cores, and also each cluster embarks a static memory or shared memory, which is basically a L1 cache, but this memory is configurable, So you can use it as L1 cache dedicated to this cluster without any L2, but you can also split this memory into an L1 cache and an L2 cache, which will be coherent between the clusters. So our the 5 cluster compose the entire chip, and the 5 cluster have each 16 cores for a total of 80 cores, and so we have also 80 core processor, basically for crypto acceleration. The board also embarks 200 gigs Ethernet interfaces. It supports PCI Gen 4. We have one 16 lane on the board, and the DDR embarked on the board is DDR4 at 3.2 GHz. Another specific part of the chip is that we have a protocol named Network on Chip, which allows very fast inter-cluster communication. So our card, the K200, can be seen also as a smart storage adapter because it can serve to many purposes. So in our case, what's interesting for the storage diode is that it's an NVMe-oF solution. It can be an NVMe solution. So it means we offload inside the MPPA clusters the network stacks such as TCP and WOPI. The NVMe drives will be connected to by PCI. So basically, it will be U.2 drives in a JBOF or FBOF. As our card acts as a root complex, as a PCI root complex, sorry. So the card also offers Gigabit Ethernet management interface and the standard REST API, which is compatible with Swordfish and Redfish. Also, as a control plane is Linux based and it has a Gigabit Ethernet interface, it can be also managed by SSH. So it should be pretty easy to develop scripts to support traditional HPC systems such as Puppet or Ansible for deployment and configuration management. Also, our board can be used in 2 different ways, which is very important. It can act as a root complex and be also the PCI master, or it can be also PCI endpoint and be inserted into any type of server or any PCI equipment which offers a root complex. Also, our last release supports both NVMe drives and SAS drives, so it allows us to build solution with mixed drives inside a drive shelf or drive enclosure. So, as we said, the K200 supports 2 modes: root complex and standalone. Root complex and endpoint. Sorry. So standalone is really to build a solution on the top of the card, which will be the PCI root complex. So typically, if you want to put the card into a JBOF or do any type of standalone equipment, such as a firewall or QoS filtering specific traffic. A few words about the performances as well. So for our NVMe-oF solution, in ROCI, we can reach 6 million IOPS on one board, and in TCP up to 4 million IOPS, which is not too bad. And so, as we said earlier, we have a control plane based on SPDK, which runs on 16 cores, and the rest of the board is a data plane. So you have 64 cores available on 4 clusters, and depending on the need and the project, each cluster can run a different type of code. So for NVMe-oF, basically the 4 cluster will be used to serve either ROCI or TCP. So one of the advantages of our card is the programmability. So it's fully programmable, and it's kind of easy to program and very efficient. You can have a separate type of program in each cluster. So it means you can use one cluster to run NVMe-oF Rocky, for example, one cluster dedicated to encryption. And you can have also two available cluster for later use if you need to scale in the future, for example. Also, we offer standardized interfaces. So, as we said, the Linux APIs are pretty standard. So, it's SPDK based. We find ports of IBVerves, .io, Open Data Plane supports, stuff like that. And also, our erasure coding implementation is based on the ISA-L library from Intel, which is also available freely. So Kalray offers a fully flexible software environment. It's completely modular, and the control plane and data plane is now based on SPDK, and it's open to partner, and we target to be an open platform before the end of year. So we will benefit of this because more and more people will be able to contribute to our code base. So here is an example of a working implementation based on the K200. So this is a Wistron JBOF called Lima, which will be available for sale at the end of this year. So it's a JBOF chassis in standalone. It's a standard 2U. You can embark up to 24 U.2 drives, NVMe, of course. There are 6 PCIe Gen 3 X by16 ports inside the JBOF, so it means you can choose to put between 2 and 6 cards inside the JBOF, depending on the number of drives and the performance you want to achieve. The base BMC chip is a standard AST 2500. And also the JBOF can be managed to a standard 1 gig interface based on the OpenBeams. So this JBOF embarking a Kalray card, K200, can be used both in TCP or Rocky. So about a few words about an efficient composable disaggregated infrastructure. So Kalray cards exploits NVMe SSD at their full capacities because of the million IOPS we can support. Also, very important, we offload the x86 from a really heavy storage stack. Everything is done inside the MPPA cluster. Our solution, as we said earlier, is fully programmable based on SPDK, and also we are future-proof and ready for the future, as everything is NVMe-oF compatible and based on the standard. So our solution can work with other NVMe-oF appliances. It was tested into IOL Labs as an interoperability laboratory. And also, it's really easy to update on the field tools through the 1 gig interface. Let's now speak about the global design of the storage diode. The idea was pretty simple. So here on this schema, you can see that on the left we have a compute node of the dark side, and on the right you have the server, the nodes which will be outside the dark side. Basically, you take a compute node attached to a parallel file system such as Lustre or GPFS, which will mount the file system locally. You use another high-speed interface directly connected to a JBOF, and somehow, so it will change for, I think, every site. Some data will be pushed between the parallel file system and the NVMe device. So it can be a daemon, it can be a service, it could be some new feature in stuff like Robinhood for Lustre, whatever, or even scripts. It's not important. So the outside node has only one interface indirect attached to the JBOF. So it will be on long distance, of course. But we don't want to put a switch here as we want security. Everything has to stay in direct attach. The design looks kind of easy, but what exactly happens inside the JBOF, and also with the block level access only solution, there is a problem about locking at the file system level. So you can't do whatever. You have to do be really careful about what you do if you don't want some data corruption in your data. So inside the JBOF, we will separate the data path using dual-ported drive. So one path of the drive will be used for the write access, and one path of the drive will be used for the read access. And also inside the JBOF, we will see a bit later, but we can choose a fully separated solution or have some resiliency depending on what we want to achieve. So about FBOF parameters, so we use the two dual-ported drives to ensure the flow separation, of course, between the two physical paths. Here on the schema, you can see the light blue represents the FBOF or JBOF. In front of the appliance, you will find some K200 cards, which are basically NVMe-oF, Rocky, and TCP target controller. These cards internally are connected to a PCIe switch. In this mode here, 1/16, and this switch will be connected only by one side to the U.2 drive, and the other card has the same access to the same drive, but through its other path. And between the PCIe switch, there is a management CPU, which allows us to manage things such as hot plug or failure or this kind of thing. So this is a fully separated access to the drive, and you can also change the PCI bifurcation depending on what you want to achieve. If you prefer to have redundancy internally inside the JBOF, it's also possible. So it means that we can have some separation at the PCI level or resiliency. So depending on the use case we do, we can adapt this to customers, which is pretty cool. So the provided solution. So just to summarize again, so we have two nodes connected to an NVMe target controller. The two nodes are in direct connect. We don't want any fabric. So one node is connected as read and write. The other node will be connected only as read only. So it guarantees separated data paths, and the protocol used will be a block level, of course, because it's NVMe. So there still needs a file system or a file system using internal locking at file level or containers. So HDF5 has been chosen for the file representation, and we built it on the top on an XFS file system. And to do that, you have to not to hack, but to do some specific configuration and modification. So you bypass the entries and the local cache of your Linux node. Other solutions are also possible, but what is important here is that HDF5 has its own lock mechanism internally inside each file. So we won't have any access issue from either the write node or the reading node. So the architecture overview. So here on the left, we have the node A, which will be inside the dark side. It has read and write access, and it will be the HGFR writer. It's connected in direct connect by NVMe-oF to our K200 board. And the K200 board is a PCI complex and serves the U.2 drive. The other port of the card is connected to the outside node, here on B, for the read-only access, and so this node will act as an HDF5 reader, and it works because it has built-in lock mechanism. So any file, which is still being written, has a lock internal by the writer, and so as long as the lock is on the writer, nobody can read. Also, this allows us to add multiple reader. Our card supports different modes of Ethernet. So by default, you have 100 gig, but you can also use cable splitter into multiple to have multiple reading modes. So for example, you can split 100 gig into 5 times 25, 4 times 10, depending on what you want to achieve. So the key elements of this design is that it's ideal for warm workflows. So just as a reminder, warm is for write once, read many. And it's hard to say exactly how many drives you need or how many boards you need, because it's really going to depend on the size of the data which is written, how many files also which is written. There are many small files or a few big files. So it's a balance to find between the three parameters here. So the number of writers, the number of drives, the IOPS you need to achieve in write and read, and of course the number of readers to a single target. So let's talk about the key benefits. So there are three main aspects of this solution. Is that it's security focused, so we guarantee a read-only access from the outside world, as the node is in direct attach. And on the target side, you can control who and how it connects. We ensure that even in the worst case of someone has access to this node and has bad intention, in the worst case, he can access and maybe ping the target controller, but won't be able to do much more than that. So the parallel file system namespace is totally hidden because only the compute node pushing the data to the NVMe-oF target has access to the parallel file system. Also, you can restrict NVMe access at the NVMe level thanks to ACL. And so the second point, which is very important on the solution, is that it's scalable. So it's really easy to scale. And we offer the possibility to start small. For example, maybe one drive and one card. And on the top of that, you can build an entire solution and make it grow. So you can add some cards, you can add some drives, you can add writer nodes, you can add reader nodes, or also you can stack full diodes just to add more storage and more IOPS to your system. Also, it's future-proof as MPPA is fully programmable, so it means we can deliver code base on a regular basis, depending on the NVMe evolution and the speed of our development, of course. As we said, it's easy to update thanks to the management interface. And also for researcher or people who want to really dig inside MPPA, it's also possible to add custom code inside the cluster. So if you want to add some feature or extra security, such as filtering or erasure coding, stuff like this. So thank you for following this presentation, and I will be available on Slack to answer to all your questions. Thanks a lot.